Let's talk about clastic sedimentology. Let's get our drink first. All right, so very specifically, we're talking about the transport of clastic detrital grains in a sedimentary system. So one, we have turbulent flow versus laminar flow. Laminar flow is what we're going to expect at lower velocities where the fluid, water or wind, is flowing in like sheets. The flow direction of the fluid at any given point is going to be roughly parallel with the transport direction. That's going to be this laminar flow. So if you've ever seen those tests where they have the car and then they run the smoke over it and you see the parallel lines of colored smoke going over the car, whatever, that would be laminar flow. All right, that's one type of flow that we get. As velocity increases, the internal shearing of the fluid increases the likelihood we're going to get something called turbulent flow, where at any given point, you could have a vector of which way the fluid is moving, could be in any direction at a variety of speeds. Now, overall, there is a transport direction in one way, but within the fluid, there's this wildly turbulent situation. So if sediment gets caught up in there, the likelihood of it settling out is much, much less. So the second part is to talk about something we call the settling velocity. How fast will sediment settle down through a fluid and then rest on the floor? So the way I like to think about this is if I had a jar and I put a little bit of gravel, a little bit of sand, a little bit of silt, and a little bit of mud and shook it up and set it down, the pebbles would settle instantaneously, very quickly, within less than a second. That demonstrates the high settling velocity because they're large, they're dense, they're able to settle right down through the fluid. The sand would be next, the mud would be last. In fact, the mud would stay probably in suspension for a very long time. We have two forces at play if we think about just a single grain of sediment dropping through a fluid, right? There's one, the force of gravity pulling it down, and the second is the drag force. Now the drag force, you can almost think of it as the same as wind resistance on a skydiver. It's the force pushing back, slowing the grain as it descends. So in a way, the grain is reaching its, quote, terminal velocity as it settles down through the fluid. So that force drives it to reach its maximum velocity. All right, so here's what's critical about this. The equation for the drag force is really straightforward. It's 1/2 the density of the fluid times the flow velocity of the fluid moving with a drag coefficient, and then you would include the area. All right, now area is really important here. The area on a tiny round sand grain is going to be wildly different than a flat grain. It's almost like a parachute. So a small mica grain could be significantly larger than a sand grain, the same weight, everything else the same, except for the shape of the mica is going to increase the drag force as it settles down. So what that means with this equation here, with the flow velocity, if you were to increase the area of the mineral, the effective area, you could have a much lower flow velocity and still have the same drag force, the same force that is fighting against gravity, trying to get those grains to settle. And so what that means is that flatter grains or grains with a larger surface area are going to stay in suspension, are going to fight settling at lower velocities. But a way to demonstrate that with quantitative numbers is through a chart called the Holston. One way that we can demonstrate that is through the Holston diagram. I messed that up. It's the Holstrom diagram. Let me explain this real quick. On the y-axis over there, you've got flow velocities. On the x-axis, you've got grain sizes. This shows the relationship between flow velocity, grain size, and then whether a grain will be picked up, transported, deposited, or eroded, right? Those are your options. So you have to kind of erode it first, and then you can transport it. And then when the velocity is high enough, you can get erosion, and then you can transport it as long as it is above the velocity required for that grain size. Once the velocity drops below, then you get deposition. So let's run through a scenario here. All right, let's imagine we have a gravel, and that gravel is in a river. Occasionally the river velocity goes up higher to pick up this little gravel, and okay, most time it's not. So that means that gravel is going to stay down, not moving, in what we call the bed load of the river. Now imagine we get a flood. A lot of water comes through. The water velocity kicks up really fast. The pebbles are going to be able to be transported until that velocity comes back down, and they're going to be deposited wherever they were transported to. Now, let's go to the other side of grains. Let's go way down here into the mud range, all right? So the first thing, if you notice, there's this unconsolidated versus consolidated mud. Unconsolidated muds are a little bit sticky, so they have to kind of be eroded initially to get them in transport. Now, consolidated muds, they can be very sticky, internally cohesive, and so they really need some high velocity to pick them up, but once they do, you can transport them much, much further. But they have this kind of threshold that you have to get to before you can rip them up and start moving them. Now, same thing, right? At lower velocities, the mud is going to be transported, but we're not necessarily going to pick up new mud because there's that internal cohesion in a high flow event, or even potentially, let's say, one river. And one the cut bank of the river, you may have higher velocities than the point bar. So if the velocity is higher for whatever reason, you might be able to erode temporarily, but you're always going to be transporting. When that velocity goes down, you're not going to be able to erode. All right, this chart just gives us a very quantified idea of velocities and how they respond to grain sizes. All right, so let's look at sand. And think about this river. Let's say a river has a variety of grain sizes in it. Mostly sand, a little bit of gravel, a little bit of silt, and then it has a variable velocity through time. The box would represent kind of normal conditions and the grain size we see. At low conditions, you're going to not be moving the coarsest material. You're going to be transporting everything out. So that means if this other sand gets into the system, it's going to get washed clean out. At high velocity times, you're going to be moving everything, right? And then the velocity goes back down. You'll start to deposit these coarser grains down here. And so what would be left in the rock record from our viewpoint would only be the stuff down here that's in that deposition. We have to have the deposition for that to show up for us in the rock record. The other sediment could have been there and then has been washed out and transported away through the system. All right, so that's really important to think about. Now, let's talk about all the forces at play when we start transporting a grain. All right, first you think about the flow of the water. All right, that's going to physically be able to move a grain. Now, as it's doing that, we would call that traction transport. It's physically pushing the grain. All right, that's one type of transport. And that would be what we call bed load. It's moving it along the bed. It's moving it via traction. And we could either think about that as bulldozing or pushing the grain forward. Could also roll the grain, but that would be our bed load. The sediment never leaves the bed. It's being pushed forward. Let's think about that same sand grain. As velocity gets a little bit higher, we might be able to move into the realm of what's called saltation. Saltation is really cool. And so this process is driven by Bernoulli's principle. If you're flowing a fluid around a surface faster on one side than the other, then you're going to get this low pressure area on the side that has the faster movement. Right? This is how an airplane wing works, right? You have an airplane wing, the air moves faster over the top, you get low pressure and you get lift. This works the exact same way with sand grains at the bottom of a river or any sedimentary system, right? You have a sand grain, the fluid is hitting, it's moving faster over the top because it can't really move very fast underneath because it's against the bed of the channel. So the fluid can't really move fast down there. There's friction involved, so it slows down. So it moves much faster over the top. That creates a low pressure zone, and that means it can lift the grain, all right? So when you get that lift, immediately once you get lifting of the grain, you lose that low pressure system. So it ends up kind of flinging the grain. The low pressure lifts it, the low pressure disappears, and the grain just kind of jumps and hops and skips, all right? That's the process of saltation. Now, let's go one step further. If we're able to increase velocity on the same sand grain a little bit more, not a little bit more, a lot more, we can create such a high flow that the water's moving, it's picking the sand grain up, and it's keeping it in suspension. Now, this is far more common with muds and silts than sands, but it can happen, right? We just need high enough flow. So the sand is in suspension. It can never settle through the water column, so it's just in suspension. It will be transported out of the system because it's in constant transport in suspension. There is another type of transport called dissolved transport. That's probably, we're going to kick the can on dissolved load, but the dissolved load is something that's physically dissolved in the water column. So to get it to turn into a rock, or even to turn into sediment, we have to step into our chemical sedimentary system thought process.